Can you hear me? Yes. So first of all, thank you very much for attending, those that are attending here in person and also on stream. It's a great pleasure to start this 7th ENES workshop, and after all this pandemic and everything, to meet you, some of you again. It's really nice. So now we will start. I will start first with a presentation with the practical details that for those that are attending here, some also recommendations for those that are on stream, and then Paco will do the official introduction and the welcome. Okay. Thank you. Okay, so we are, as you've seen, in Rectorat UPC Sala de Juntes. The coffee breaks and the lunch will be served in the next door here in the library. And what we recommend is to use the terrace outside. We have a very nice place to have all this beverage. And please, it's not allowed to enter drinks and food in the room. We also ask you to sign the participants list each day. This is something required by the Commission. And toilets are here left from the meeting room in the same first floor. Something also important to you to say, please don't leave the belongings unattended, mostly outside the meeting room. It's better to say that to have a bad surprise afterwards. So in the room, I would say no problem. We will close for lunch, and also there will be always someone from us. But I would say if you can avoid, if you are living here and avoid leaving your purse or whatever, your bags, I think it's better. And finally, we will do a group picture tomorrow before lunch in the stairs. So. We will warn you, and we will go down everybody, and we will take pictures to have dissemination material. And also, it's possible that the streaming will take you on during the workshop, and you appear on the streaming signal. Then regarding the interaction, so please the in-person speaking should come here for the talk, and chairs will be in the main table too. For questions and comments, use the Google Drive document. This link has been sent to all participants, and there is a Google Drive for each session. Session chairs will take the questions from the document and we'll ask to the speaker. And for us, it's very interesting because we record, and somehow we have written the answers.
Just that the Google document link has been sent to the remote participant, but it's going to be sent now by Sophie Morellon to all the participants.
Okay. Thank you. Sorry, yes, we only send to remote. And also, speakers, please upload your slides before your session. You have some mails asking on how to do it. Regarding social dinner is next to the beach in the Arenal restaurant. You have in the website, you have the address. It's called Restaurant Arenal. And for those who want to leave from here, there will be one group at 7:15. We will leave here and we will go together. If you want to go yourself, you have the address, and with Google Maps it's quite easy to reach. And finally, last point, there will be some Mare Nostrum visits organized last day on Wednesday after lunch. If you haven't been there, I think it's nice. Even it's our HPC, but it's inside the chapel next to this building. So there will be 3 groups. Please, there is a list outside. Write down your name, and then we will do the visits after lunch. And ya está. And if you have anything else, any question, please contact me. Yes, Jean-Claude.
Is there any password for the Wi-Fi?
Yes, sorry, I did not put. There are regarding Wi-Fi. There's here the name. EduroAM should work, but also you have the one for the room. And, yeah. So Paco, please.
Okay. Thanks, Kim. Welcome everyone. It's very nice, as Kim said, to have people here. My name is Paco Dobles Reyes. I'm the director of the Earth Sciences Department here at the Barcelona Supercomputing Center. I would like to start by thanking all the people who put their time and efforts into organizing this. You and Albert and Sophie and many others that have been really working on having an agenda and having people in person finally in a place so that human interactions can come back again. Just a few words to introduce what the BSC is. The Barcelona Supercomputing Center is a public consortium funded by the Spanish government, the regional government, the Generalitat de Catalunya, and the Universitat Politècnica de Catalunya as well. So it's the local university. Actually, this building belongs to the university. We apart from providing supercomputing services to the community here in Spain and in Europe through the PRAISE program, and in the future through the EuroHPC program, there is a lot of research done at the center. There is now 800 employees working at the BSC, and I would say that something like 70% are researchers and technicians supporting that research. And it's also a place where training is taking place, not just through the PhD programs that are being implemented here, but also through the participation on training activities at the international level and also at the national level here in Spain. As I said, there is research performed at the BSC. It's one of the key activities in the center. There are 4 research departments: the Computer Sciences Department, which is the largest one, and historically the core of the BSc. But then there are also 3 departments working on applications of supercomputing and data analysis. The Life Sciences Department, working on a wide range of issues related to life sciences, and including, for instance, natural language processing. The CASE department, the CASE department, it's a department working on engineering issues, and they work on applications that have mainly to do with requirements from the private sector. And our department, Kim and my department, the Earth Sciences Department, where around 100 people work in trying to bring the supercomputing capabilities and evolution of the computer sciences to our field, to earth sciences, addressing mainly problems in the weather, climate, and air quality arenas. And somehow we are around 100 people working on mainly these 3 fields, weather, climate, and air quality, but with a very strong service-oriented interest. So we have a group working on Earth system services that are trying to bring our research closer to what society is actually interested in. And I'll leave it there. So.
Thank you, Paco. There was a slide thanking all the organizers, thanking the technical committee for preparing and selecting the speakers and everything. And then also I would like to thank you, Gabriela, Albert, and Sophie Morello in the distance, because all the work that they did to set up this workshop. And yeah, and let's start and enjoy the workshop. Thank you very much.
Okay, so then I guess it's my time. So welcome from my side as well, and thanks to Kim for making this happen here. I had the honor to, so my name is Joachim Bierkamp from DKZ, by the way, for those who don't know me. And I had the honor to organize 2 of these ENES workshops. This is the 7th now. The last one had to be virtual. So this one is face-to-face again. And what I might mention as well is we already planning for the 8th and the 9th one. The 8th in organized by our colleagues in Lecce, hopefully if we get the funding, and the 9th one in Stockholm by Swedish Met Office. And today here I'm sharing this session on our HPC environment together with Jenni here, who will introduce herself in a second. This session has 6 talks. 3 of them are on site, 3 are online. And it's basically 3 parts topic-wise. The first 2 parts are on the European HPC ecosystem. So first of all, Bastian will tell us about what is the EU strategy to support applications on HPC. Then we'll have a talk by Jenni on the first European EuroHPC pre-exa scale system. Then we will look a bit into Asia and have 2 talks related to HPC for climate in Japan and China. And then the last 2 talks are basically touching upon the two ends of the spectrum of things which we are fostering with our infrastructure. One is a really capability-driven destination Earth thing, where we really want to do things which we cannot do right now and leverage exascale capability for that, and capability. And the other is about really using what we have right now, models for CMIP exercises. And so without further ado, I would like Bastian to step up here. And I think questions are organized only via Google Docs, or can people... Preference is Google Docs, okay.
I will unplug this now and hope this works.
No, it's, we have your slides.
Ah, you have my slides already?
Yeah.
That's perfect.
Yeah, it's very cool.
So you want to avoid that, do some last minute changes. Now I have more slides, notice. Okay. And this one works? Yes. Yes, sorry. Okay. Somehow this... Cool. See it here as well, so... Hello? After this, sorry. So many thanks to invite me to come here. I will give you some, let's say, rough information about something which is highly complex, especially as it currently covers 33 nations in setting up competence centers, 1 in each of the nations. I will go through this quickly. I will be here around these 3 days, so in case you have any questions, then you can also grab me later, or you can be upset because I'm still here and just had this boring talk. Let's see. So the idea is really to give you some information about something we're doing, which is called the National Competence Center Initiative. So as I said, 1 per country. Give you some update on what happened so far, and give some insights about the rationale why we are doing this at all, and what the benefit is, and what the benefit for the HPC community is. So in general, what happens there is that we build systems currently in Europe. We have petascale systems, we have European pre-exascale systems. People are already spending in their minds the money for the exascale systems, and obviously there's always the idea, especially of the funding agencies. So we build something, we put it there, and then all the people will come here and are happy. Obviously, when you, as I do, are managing a center, obviously all the customers are always happy. But there's much more behind the whole thing. And there's a question, let's say, what kind of competences do we need in Europe really to set up the systems, the ecosystem in a way that it really matches to the users' needs. And I know that many of us, especially also Barcelona here, they know very well their customers. But we have some new players entering the field now from different areas, technology areas, from the application areas, and they need to understand really what it means to make it much more efficient and to fulfill here, support the European strategy. So what we learned these days when setting up these 33 national competence centers, I usually like this quote from Rumsfeld from 2002, that we have known knowns, so there are things we know that there are known unknowns, which is also fine. And but the interesting part are the unknown unknowns, which we have to face every day with our work, and especially the more complex and the more also political the whole aspect of HPC and the applications and training and everything around that gets, the more we learn how challenging it is to really set up a European HPC strategy. So competences, yeah. This morning I learned, for instance, so I have a competence. I have a competence that usually when I go on business travel, I take some time to have some walk around the city. So starting early in the morning or something like this. So if you have seen me like 20 minutes ago arriving here, you might have found out that
I have still my competence level of 2 years ago, overestimating my time to walk. So it was a bit in a stress phase. And yes, I could need some training and some understanding and some recalculation of time. For all of us in our fields, it's always the competences. We need skills and we need, let's say, certain expertise to do our job. So the competence is the ability to do something well. And it's not necessarily attached to a certain domain. So obviously, when we are going to the climate research, we have competences here. We have, let's say, similar competences in some parts when it's about technologies. We have, let's say, different competences when it's really about different application domains. And we always have to be clear that this is something which needs a long learning phase and with trial and error. So this morning was not a complete error, but let's say it was some room for improvement for me. So yeah, competences is something we have always, let's say, first of all to get and then to maintain. So why I'm saying this? So if you look at competences, I guess most of us are, let's say, active on the European level, and we all know that sometimes the European level of action is quite different from the national level. So when I talk about 33 nations, these nations are quite diverse and mature in their setup of HPC and what we call the associated technologies like AI or HPDA competences. So national level, you have national infrastructures, national applications, national training, national research knowledge, and diverse other activities. And they heavily depend on the investment which were made. So we have some countries in Europe where heavy investments were made the last decades. So yeah, let's say the systematics there and the processes are obviously much more mature than in countries where HPC is more or less a new field and they are entering this. So on one hand, you can keep this and say, okay, yeah, but on European level, there are some lucky people from these nations which are not mature. They can enter the European level and they can learn something. But if you want to have really a big baseline in Europe, then you need to build some bridges. So you need to first of all, enable those countries which are not that mature, which is nothing negative. And this is, by the way, an interesting experience because many times people think it's a bad thing to say, we are not so good in this, but with the competence center activity we set up, we want to close this and support them. If they're not that good yet in the one thing, they can simply try to use synergies from other centers. So the idea is about building bridges and really to see, let's say, how we can get higher or increase the level of competences throughout the different nations, and obviously then by that strengthening the European level. So how did we address the challenge? So obviously there was an idea, let's do competence centers. That's always how it starts. Then you ask, okay, what exactly do you mean? Yeah, competence centers. So we discussed, we worked, and first thing, as I said, we have to consider the different levels of maturity. That's the most important part. The second phase is to create somehow a structure to identify the existing competences, so what is there, and to provide a framework to establish the NCCs. So here it's already getting interesting because you have two levels. One level is the European level, so this is about, let's say, interaction of the NCCs. The other one is the national level. Competences are easily identified if I'm asking a center X, because then they tell me exactly what competences they have. They will not tell me exactly what competences the other have. So this is somehow a culture change in this competence center because it should map the whole country and not only a single participant. Again, the second mission was then on the European level to support the stimulation of national development and to strengthen the European level. How did we start the whole thing? We started now with a 2 years activity which focus on commonalities. So one part is obviously trainings and skills development. And yes, many of you may raise the hand now and say, yeah, but Praise is already doing this, and High Peak and whoever. And obviously, yes, that's true. But we're seeing here, let's say, a training portfolio which goes beyond that of the participants in one or other activity, because we want to map the whole thing. Still, we will not start from scratch again. So there were, let's say, discussions in advance. We discussed with Praise, we discussed with the Focus COE on the Center of Excellences, we discussed with the different players here, so to have one common portfolio. Again, it doesn't make sense to reinvent everything again. That's a mistake which has been done or been performed too often. Another part is technology transfer business development. Hot topic, industrial collaboration. If you remember that if you will build it, they will come. There are expectations that if you build a system somewhere, immediately 100% of the machine is used by industry. That's a challenge. It's a rather mission impossible. Because simply it's like the industry has certain needs, and we have countries which work with industry, but even there, if it's not, let's say, a system especially tailored for industry, funded by the industry, then it will not work like this. However, still, you have a system and you can give parts of that to the industry, but you need to understand what that means. And that's the idea here. Those countries which have the experience, let's say, share the knowledge with those which don't have the experience. Competence mapping is very important. As I said, we want to look at the national competence centers. We want to understand what is there in the nation. So what we do is simply, we do a map of competences. And this is something like a growing document or documentation. So whenever somebody is identified, independent, if it's an academic partner, if it's an industrial partner, or who else, they can join the competence initiatives in their country, and they are mapped also on the European level with certain competence. At the end, the portfolio of competences of the national competence centers is inherited by the competences of the participants there. Then we have the facilitation of scientific technical expertise and the awareness creation. So the phase 1, which was now 2 years and will run until end of this year, we adopted a common approach. Simply, let's say, a clear structure. If you know the projects, it's like a work package for each NCC. Coordinating a project with 34 work packages is not fun, I can say, but I'm still alive. This simplifies the interaction because they have certain topics there. So this is the example structure of an NCC. To do some competence mapping, you identify the ones from science, industry, society, and politics. At the same time, there are also, let's say, the requirements giver. So there could be end users of those, but also service providers. And then you work out, let's say, what the NCC could be set off. They work on a structure, and they want they should, let's say, establish a legal entity in a certain time frame. And then you see, let's say, if you have 33 national competence centers and try to make them all interact with each other, and these are only 10, which you see here. So imagine the whole picture with 33. It's getting complex, but it can work. So what happens here is that we in each NCC, we have one or more experts in a specific topic. We call it a champions principle. The term champions is heavily discussed, so I like it. I like heavily discussed items. Because for me, they are all champions. So the idea is that we bring these people together, those people which are responsible for the certain aspect. And what we did here is there's a coordination support action which supports this. We provide a forum, do working groups on European level where they are all invited to. We make, let's say, joint events. And then at a certain point in time, they can split off in satellite activities. So not necessarily all the 33 have to discuss about everything, but the idea is to bring them together to find and to discuss about certain actions here. The NCCs are involved in the selection and definition of workshops, so it's not like that somebody like me says, oh, it's a good idea to do that and that. It has to fit their demands. And we have some working groups on training, twinning, mentoring, industry interaction, awareness creation. It now is already, let's say, getting bigger. We will have one on legal aspects. This includes IP issues, but also, let's say, legal aspects, how to set up structure, etc. And the idea is really that we develop here the best practices that can be adopted by the NCCs, provide the access to the knowledge, and facilitate the discussions and solution finding. So I quickly go through this because I don't have that much time. As I said, this is the EuroCC project, so this is the one where the 33 national competence centers are implemented. You see the countries here, so more or less we have everyone on board besides some exceptions. This is the coordination support action. It's smaller with some. We selected or we asked those partners to come in there where we know that they have the expertise, long-time expertise in certain fields, and that they can, let's say, staff such working groups and moderate them in a very good way. If you look at this, what happened so far, and the numbers are always good, but let's say the quality behind this is also good. So this is much more important for me. like 50 workshops have happened, 85 training courses organized, and 75 interactions with industry have been set up, which is good if you look, especially as some of the NCCs have not worked with industry beforehand, and this is something like the first step forward. So the competence mapping and this picture is something you can find on this website, which I just showed to you, and I will show it again. This is the EuroCC access domain. This is the portal that we're setting up. You can find there information about the NCCs. You can find also the competence mapping and look for competences. It has just been relaunched, so if you find some error, which you definitely will do, just inform us with a quick message, and then we can deal with it. So far, we have 153 detailed competences identified. There's still, let's say, in terms of analytics, but we wanted to have something out there and not, let's say, discuss until we have the Swarovski edition of solutions, which at the end is then 3 years late. The aim is really to integrate these competence maps into the EuroCC access portal. The NCCs can be the single access point at a certain level. The EuroCC access will be a single access point at European level, and then both are interlinked here. So interactions with running activities, also, let's say, with the centers of excellence, for instance, which you see on the right side. We brought them together with the national competence centers. We brought them together with the Fortissimo for EuroHPC activity, which does business experiments. There was an alignment between the Fortissimo for EuroHPC strategy to ensure that as much countries as possible are, let's say, covered, and not the usual suspects get all the money here. For us, it was important that even, let's say, if a country X, which is very mature, puts in 20 bids, and a country from the EU13 state puts in only 2 bids, that they have a good chance to be funded if this is a qualitative good proposal. There's interaction with the technology providers. There's interaction, obviously, with the joint undertaking, with the ETP, and just I can give you some small spoiler here. So this is the portal to access. You will find here a lot of things, documents, which are findings of workshops. There are much more findings of workshops, but not all of them are public. So there's an internal NCC page where they get much more information internally. There's a funding opportunities overview. There's a video library of events which have been held with vendors, with, let's say, strategic initiatives. And if you do an outlook here, to give you a short outlook here, and this is also interesting for the application field because obviously EuroCC and CASTIEL end now at December 2022. There's already a new call published, which is, I think, not opened yet because of technical issues, but the deadline is approaching, yeah. And this time, this should also cover the coordination of the centers of excellence. So something which happened before in an extra CSA, and there was a request to merge these two activities now. What we see is, and what we already get a feeling for is, let's say, with this establishment of the NCCs, we really promote the use of HPC and associated technologies in Europe. We're creating success stories. That's important, and this is something that each country can take. Even if it's a success story from another country, they can take it and give it to the funding agencies and look, this is the possibility if you invest in this. And that's very helpful, especially for those which don't have, let's say, this kind of lobby yet in their countries. And obviously, we will also work on providing guidance to ensure the best possible use of the PETA, the pre-exa, and later the exascale systems, the capabilities. An important part, again, is competences. It's not only in terms of technology. It's not only about that I know what an ARM processor does or something like this. It's about everything around the utilization of this. And obviously, one of the most important parts here is the interaction with potential users. Industry has a different language, and things have to be done in that proper way, but it's only possible if you know the people which have the expertise already. Okay, that's it. I hope I was not too long.
No, that's okay. Wonderful. Thanks, Bastian. So we just looked at the Google Docs. We have no questions in the Google Docs. So yes. I have a question, Bastian, because you said, you already mentioned this kind of working or getting to work together all these different players. And it's the example of training, for instance. I mean, for the centers of excellence, for the new proposals, we were asked to set up training, to propose training activities. So we have several centers of competence proposing training. You have praise, you have us. So how do you expect to get this somehow channeled?
This is something we started already with, let's say, the interaction with praise and the others. So obviously we use one common registry for now where we put in all the information from the sets. then there's the awareness creation. Obviously, if you as a center of excellence do something and you don't make people aware, it's most likely that they will reinvent it. So an important part is, let's say, to bring the NCCs, the COEs, PRAISE, and whoever will be out there together to look, okay, what is the current portfolio, and really to have this discussion once you're working on a training course to announce this so that the others know, okay, there will be something, and in an ideal case, they could even contribute to yours instead of doing something else. Again, it depends always if people want to collaborate.
Yeah,
this is something which is out of my hand.
Yeah, you need to give them a place also to collaborate.
Yeah.
And another question, is there any questions from the audience? I've one more. Regarding your champions, or we say the people with specific competences, do you have identified people with specific competences in climate and weather?
To be honest,
modeling?
we did not go in that direction. So far, it was in this frame here.
Okay,
But
it's more MPI.
No, it's rather, let's say, now for training around this, but not, let's say, with specific topics. Mm-hmm. It's first of all, let's say, on the level of not bringing the applications together, because so far this happened more or less, or should have happened in the focus COE area. This is the next step for the next time, that we also look at the topics, the domains. Obviously, they have they provide some competences and say, okay, in this country we have competences for certain topics, and this is something which will evolve now. Yeah.
Okay, Luis, had a question?
A pretty ugly one.
I have to leave now.
I'm a user, and I run into the trouble that more and more computing centers require two-factor authentication, and I would like to do automatic transfer of data. So I need to have a robot at home who is typing in on one token a number for one side, and the other one a token for the other side, and I need to trigger that from a Slurm job to get an automatic data transfer. Is there competence and a solution for?
To be honest, we're working on something like this, but not your robot at home, so you will not get a robot from us.
So the problem is that all sites need to join this attempt, and not each one should do its own solution.
Yes.
And unfortunately, what I can see is that everybody is working on its own solution.
Obviously.
So we are kicked out of working on all systems at the same time. And if you are not lucky living in an institution where the computing people are a little bit more collaborative or cooperative, or more looking into the future to handle that in a proper way, you easily can close the whole business.
I know.
So that's just an ugly question regarding competence of supercomputing centers, which are failing developing proper authentication algorithms.
It just give it back to you. It depends. If you're a computing center which has a certain requirement, like an ISO certification, it might be that you run into trouble, that you would like to do it for you, that you're happy, but you cannot do this. It's a question of the setup of the centers themselves in that regard, but this is also something where I agree with you. There has to be exchange on finding the solutions, but I would be too I don't know, positive is probably negative, don't know, to believe that each and every center will have the same, let's say, will set up the same structure in case it does not fit to the operation model. That's the problem. They have to keep the individuality in that regard, which means that they're probably excluded from something, or they exclude themselves from something.
One comment on this. I remember that there has been projects funded by the EU to solve this problem. 25 years ago, 30 years ago.
Yeah, there have many projects funded to
nothing is left over of this. If I would be the European Commission, I would definitely ask, you solved this problem already 30 years ago. Where is the infrastructure for, so that we can build on top of it?
I think I know which project you're referring to. Or projects, let's say it that way.
Okay, let's take that.
We can discuss on the coffee break.
Let's take that to the coffee break. Okay. Let's thank Bastian again. And now I take over.
Yeah, I can just mention that there are at least some questions in Google Docs, but I'm sure that you can answer them then after the session. Now? Yes.
Okay. Sorry, didn't see that.
Yeah, okay. No, but they just came. Okay, I can then.
Yeah, move
yes.
on. Yeah, just okay. Okay, so you introduce yourself, Jenni, please.
Okay, yeah, sure. Okay, so hello. Okay, I will move on in front of the mic. Okay, now it should be fine. So hello, so I'm Jenni Kontkanen. I'm actually started just this year at CSC, IT Center for Science in Finland, where I'm working as climate strategist, which means in practice that I'm working on different atmospheric research or climate research related projects. And today I will introduce you Lumi, the first European pre-exa scale system. And yeah, I guess I can change the slide from here. Yes, so in the talk, in the first part, I will tell the story of Lumi so far. And then in the second part, I will talk more about Lumi capabilities. So first, as a bit of background about the EuroHPC initiative. So the EuroHPC joint undertaking pools European Union's and national resources in high-performance computing with an objective of acquiring and providing a world-class supercomputing and data infrastructure for Europe's scientific, industrial and public users. And at the same time, the aim is to support an ambitious research and innovation agenda. And this EuroHPC declaration has been signed by 32 European countries. And the first generation of these EuroHPC systems was announced in June 3 years ago. And then in this first generation, 3 pre-exa scale systems will be built in Europe. So one in Finland, and this is of course now this Lumi that I'm talking about today. Then one in Italy, so this is Leonardo in Bologna, and then also one in Spain, which will be this Mare Nostrum 5 here in Barcelona. And in addition to these, 5 beta-scale systems also are built or will be built to Czech Republic, Bulgaria, Luxembourg, Portugal, and Slovenia. Next generation of EuroHPC systems are then planned for 2023 and 2024. So Lumi is our EuroHPC system, which is funded by EuroHPC and Lumi Consortium. So Lumi Consortium is a unique consortium of 10 countries with strong national HPC centers. And you can see the Lumi Consortium countries in the map, colored with the blue color. Also there the countries which have signed the EuroHPC declaration are colored with this bit darker gray. You can also, with this white spot there, see the location of CSC data center in Kajaani, where Lumi is located. I will talk more about this data center soon. And so the resources of Lumi will be allocated per the investment to Lumi. So the share of the EuroHPC is 50%, and that will be available for all European researchers. And then the shares of the Lumi partner countries will be allocated by local policies. So these are kind of handled as extensions to national computing resources. Okay, so Lumi, when it's fully operational, it will be one of the fastest supercomputers in the world. It's an HPE Cray-X supercomputer manufactured by Hewlett-Packard Enterprise. And it has a peak performance, or will have a peak performance over 550 petaflops per second, which will make it one of the world's fastest when it will be its full capacity. So fastest today is Fugaku in Japan, which has a peak performance of 513 petaflops per second. I think we will actually hear about Fugaku in the next talk in this session. And then the second fastest is Summit in US. And if we think about what this 550 petaflops per second would mean when comparing the normal laptops, that is equivalent to about 1,500,000 modern laptops with respect to computing power. And physically, Lumi is the size of 2 tennis courts. And it's a modern platform for high-performance computing, artificial intelligence, and data analytics based on GPU technology. So I will talk more about this then in the second half of the talk. So Lumi is designed as a Swiss Army knife kind of tool that can tackle a wide spectrum of use cases within different user communities. And this way, Lumi can enable also top-level scientific breakthroughs related to, for example, climate research, data science, plasma physics, life sciences, material science, and humanities and social sciences. In addition, Lumi will have a fast track for urgent computing needs for time-critical simulations, which could be related to some national or European security or other major crises. So, for example, pandemic. But let's hope that we don't need pandemic simulations soon again. Yeah. Okay, so then about Lumi data center in Kajaani. So Lumi is located actually in the premises of an old paper mill. You can see that there. And this is the hall where Lumi is nowadays located. So this is how it looked like after the paper mill had been shut down, like in early 2000s. And then this is a schematic showing how Lumi looks like there. Let's hope that we can soon get one video working so you will see how this Lumi and the data center really looks like now. So actually this old paper mill provides very good facilities for a data center. So there is 100% hydroelectric energy up to 200 megawatts. There is very reliable power grid. So in the last 40 years there has been only 1 2-minute outage. There is free cooling available thanks to water. And also this waste heat is reused to heat the district around. So actually around 20% of the Kajaani district around Lumi is annually, or like about 20% of the annual heating of this district around Lumi is covered by Lumi. And of course, if they would be normally heated with some fossil fuels, we can even calculate there some negative CO2 footprint for Lumi in that sense. And although Kajaani is quite far away physically, it's also Kajaani data center is very good connected, so it's a direct part of the Nordic backbone. And there is also elevated security standards at the data center. Okay, and now let's hope that this video works. So it should show you how this. Yes, it works. There's no sound, but there's only music, so it's fine. So you will see how Lumi looks like. Yes, so as you can see, they have made Lumi look also really pretty outside, but although unfortunately I didn't yet have a chance to go to visit in person due to this COVID, but maybe soon. Okay, so then next I will talk about more about what Lumi has inside it, so about Lumi capabilities. So Lumi is a tier 0 GPU accelerated supercomputer enabling high-performance computing, artificial intelligence, and high-performance data analytics. Lumi has several partitions which are connected via high-speed interconnect, and there is a possibility for combining different resources within a single run. So you can use even like CPU and GPU nodes within a single job. And Lumi's main partition is this GPU partition, which has this over 550 petaflops, and they are powered by over 10,000 of AMD Instinct GPUs. Lumi also has a supplementary CPU partition with a bit less than 200,000 AMD CPU cores. In addition, Lumi has interactive partition for data analytics and visualization, then also 8 petabytes of flat-based storage layer, then 80 petabytes of parallel file system, so lustre storage. Then also Lumi O is an object storage service with 30 petabytes of object storage for storing, sharing, and staging data. And in the future, Lumi will also have a quantum processor, so Lumi Q, and then also this container cloud service, so Lumi K. And this figure illustrates the timeline of the Lumi. So the system procurement started in November 2019 and ended in August 2020. Data center preparations were ready in the beginning of 21, and then the first phase of Lumi started in the end of 21 with Lumi C, P, F, and D. And since then, Lumi has been in pilot use. There has been regular access to Lumi C, so CPU partition, and then development access to Lumi G. And now, then during this spring, this Lumi G is gradually deployed, and Lumi C is upgraded, and then the final configuration of Lumi should be ready in autumn this year with also Lumi O and Lumi K. And then Lumi should be generally available. And in addition to traditional command line interface, on Lumi, high-level interfaces will be supported, which means, for example, integrating Jupyter notebooks, RStudio, and similar software backend to Lumi. There will be also rich stack of pre-installed software and data sets provided as a service, which means these kind of curated large reference data sets that will be available and maintained on Lumi. There will be also support for handling sensitive, so for example, GDPR subjected data on Lumi. So to summarize briefly these Lumi capacities, so Lumi has an extreme computing capacity based on Lumi G and Lumi C partitions. Interactive use, so visualization, data analysis, and data pre- and post-processing is possible on Lumi D. There will be a broad stack of pre-installed scientific software, databases, and datasets, both commercial and community ones. Sharing datasets will be possible over Lumi O service and deploying microservices on Lumi K. And then in the future also exploring the quantum computing world will be possible with Lumi Q. So now, after you have heard about these Lumi capacities, you probably want to know how you can get Lumi resources. So European researchers can apply resources from EuroHPC allocation or then from national resources. So if you allocate it in Lumi consortium member country. And these Lumi resources are allocated in terms of GPU hours, CPU core hours, and storage hours. So each project is resourced a combination of these. There is no dedicated hardware, so all users can access the whole system, and all countries, or Lumi consortium member countries, will reserve shares of these pools per their share of the total ownership of Lumi. And these resources are procured in terms of preparatory access projects, development access projects, general access projects, and then extreme scale projects, which should be mostly GPU hours. And as a final note, Lumi of course also provides new opportunities for climate research. So Lumi will be one of the computing platforms of this European Commission's Destination Earth initiative, which aims to build digital twins of the Earth to support decision making. We will hear more about this later in this session, but I will just briefly mention that in this Destination Earth, two first priority digital twins will be on climate change adaptation and weather extremes, and Lumi will be one of the main computing platforms for, or expected to be for these digital twins. And more generally, of course, Lumi's extreme computing capacity enables multi-decadal climate simulations at unprecedented resolution, and also using AI and machine learning methods to accelerate climate models and for doing enhanced data analytics, and of course also much more. So to conclude, we are now living EuroHPC era, where unprecedented amounts of computational resources and capabilities are or will be available for European research and innovation. And Lumi is one example of those. So Lumi is a leadership class resource designed for a broad range of user communities and workloads with an enhanced user experience. And Lumi also provides new opportunities for climate research. So if you are interested to hear more about Lumi, you can follow Lumi on Twitter. Also, there is LinkedIn page and YouTube channel. And then if you want to know more about also technical details of Lumi, you can check the Lumi webpage. So it's lumisupercomputer.eu. And there you can also see my contact details. So you are free to contact me also after this if you have something. Thank you.
Okay. Thank you, Jenni. So is it a computer for left-handed people? I had problems to use your mouse. Never mind.
Sorry, I was a bit confused now.
Okay, that was not the real.
But Lumi is for everyone, both left and right.
Okay. No. So we have a few questions in the Google Docs. So maybe I start with the more complicated climate-related ones. So Nikolai is asking how Lumi C and Lumi G are connected.
Okay, I must say that I'm not really a technical expert, so I can find out answers to all the technical questions. So actually, director of Lumi is Pekka Manninen, and I'm sure that Pekka would be able to answer.
Yeah.
But I'm happy to find out the answers to you Nikolai. Yes.
Yeah. The question is if.
But the point is that you can use important point is that you can use both CPU and GPU nodes within a single job.
Well, basically the question if there are two separate supercomputers that happens to share the same name, or they somehow actually working together. But well, I mean, we can torture
maybe it's
Pekka
better that I
with
don't say something that I'm then
Nikolai,
regretting.
sorry. So we know from Pekka that they are going to be connected. So it's not independent machine.
Yeah. Okay.
Thanks, Mario.
So something, but maybe you can answer that one. So Reis is asking, many of us have not much experience programming AMD GPUs. And so how is CSCS geared to provide application support with respect to this aspect?
Yeah, actually this part also... so was the question, is CSC providing applications for it?
Yeah, so what is CSC doing to help people to get
Okay, now
running on AMD GPUs?
Now I fear that I also cannot answer this very well. I know that Lumi has a very good user support, at least that you can contact. That is very effective. So you can also find that on the Lumi Supercomputer webpage. As far as I understand, I also understood that these AMD GPUs can be challenging to people, but I must say that I didn't know for this presentation there was. I didn't.
First of all, the GPU position doesn't just yet exist, but I think Louis is preparing something.
No, I can give some information about the GPU work which is going on. So CSCS has put Icon into the benchmark for Lumi. And I know that the providing company is extremely hard working on getting it running, and that there will be in a couple of days, most probably, a compiler available, the first beta compiler which can compile the OpenACC required for that. And we know that the vendor who is implementing Lumi promised to port not only the 2-year-old benchmark version, but as well the latest version, and support with their compiler. So from that point of view, I think that you can be sure that almost everything from OpenACC will be supported on Lumi, so that if you have your application ready for OpenACC and it runs fine on Daint or on Joule's Booster, you can be almost sure that it will run on Lumi G as well.
Okay.
Thanks, Louis.
Yeah, thanks, Louis. Okay, yeah. And just to mention, so Jenni stepped in for Pekka, who was meant to give this talk in the first place. So, but
That's why, yeah.
but I think it was really informative, and there are quite some questions in Google Docs. Maybe you can try to find out and then answer those
I'm very
those
happy
online,
to find the answers if I'm not able to
because there are
answer them
some very interesting questions.
Okay,
So.
great.
And I do only know this because I'm one of the developer of ICANN, and Cray is directly talking to the developers of the codes.
Yeah.
So that's the big advantage we have in this case, and it might even be passing by the Lumi people. They may know that happens, but they don't know the details. So, which is totally fine in this case, because it's not really of large interest, I would say.
Yes.
Okay, good. So then let's thank Jenni once more. And
Thanks.
the next speaker would be Sam Hatfield, who's sitting there at the corner. Hi, Sam.
I uploaded a revised version of the slides. Do you have that downloaded? About half an hour ago.
No, but that next question was about try this one. It doesn't work. That's easy. Okay, so we're waiting for the slides. Okay, good. So go ahead, Sam.
Thanks. So I'm Sam Hatfield. I'm a researcher in the research department of ECMWF. And despite being a computational scientist for about 7 years now, the project I'll talk about today was really the first time that I've truly grappled with a supercomputer. So I want to begin by thanking all the people on this list here, because without their help, I would not even got past the compilation stage. So let me begin with some context. ECMWF has recently embarked on a 7-year program, you've probably heard of it, called Destination Earth. And the goal of Destiny is to run the first storm-resolving digital twins of the Earth system in an operational context. Now, I won't go into details about what a digital twin actually is, because we have a nice talk by Niels Veddy later this afternoon for that. But suffice it to say, at least from the ECMWF perspective, it's a kind of spiritual successor to our earlier scalability program, which is currently wrapping up. And there's a nice newsletter article on the left there, which describes the history and connection between these two programs. So the challenge from Destination Earth for us computational scientists is to take our existing model infrastructure and get it ready for running on various pre-exascale machines like Lumi that we just heard about, in order to do operational weather prediction at 1 kilometer resolution. On the right, we have an example, earlier work by Niels Veddy, running the IFS model on Summit at 1 kilometer resolution. He ran a seasonal 1 kilometer simulation, and these experiments really pushed the IFS to its very limits. So now our goal is to take that technology and make it ready for use, for operational use. To this end, we are at ECMWF currently running and testing the IFS on a wide variety of different HPC systems, probably the largest number we've ever run at any one time. And in this table, we have some of the relevant ones. At the top two are our operational machines, so the outgoing, which is a Cray XC40, which we're retiring this year, and the new one is an Atos Bull-Sequana XH2000. Both of these are CPU machines, although our new one is based on AMD CPUs rather than Intel. And we also have a small GPU cluster, which will only be used for testing, not for operational use. In addition to these internal machines, we also have access to a number of external machines, including 3 of the top 10 fastest in the world at the moment. For example, Jules Booster, which we are using for the NextGEMS simulations, storm-resolving simulations run for many decades. And we also are currently running on Summit with a new Insight allocation that's led by Ina Polishuk rather than Niels Veddy. We're also currently running on Lumi G, albeit the test nodes, because this is not completely available at the moment. And we are hoping to get access to Frontier when that is finished. though that is provisional based on the success of the current InSight simulations. So when you look at this table, you really have a sense of the consequences of heterogeneity. We have a variety of different hardware types and manufacturers, and a variety of different tool chains and software stacks. So we have the exact same model, and we're expected to run it across all of these machines at the same time efficiently. So this is a big challenge. At the bottom, I've highlighted the subject of this talk, which is Fugaku. Fugaku is currently the world's fastest, at least the fastest reported by the top 500 benchmark, with about half an exaflop of peak performance. Now, Fugaku is a CPU machine, so it's rather unusual in that regard for having such a high peak performance without GPUs. But these are ARM CPUs, and I'll talk more about that in a couple of slides. Now, I'm particularly interested in Fugaku because of its capabilities regarding low-precision floating-point arithmetic. Over the past few years, ECMWF has been doing more experiments into low-precision simulations. In fact, last year with model cycle upgrade 47R2, we started using single precision in the atmospheric model operationally. And we found that when we use single precision, it runs about 40%, well, it's 40% cheaper, which means that we can increase the number of vertical levels and actually get an improvement in the weather forecast scores. So we basically traded numerical precision for vertical resolution. On the right there, you can see an example of hurricane tracks simulated with double precision and single precision, and they're more or less the same, at least within the spread of the ensemble. But we don't just stop at single precision, we can go even further. Nowadays, hardware supports a wide variety of different number formats. At the top three are the ones standardized by the IEEE, the so-called floating point formats, FP64, 32, and 16, or double, single, and half precision as nicknames. And traditionally, just double and single precision had hardware availability, but now CPUs and GPUs are coming online, which support also half precision natively, not just for data storage, but also for computation. Now, hardware vendors are not constrained by the standards, and many of them are implementing their own data formats, like the bfloat 16, which is pushed by Intel. This is another 16-bit format, which swaps some exponent bits for significand bits, and they claim that this is very good for deep learning inference tasks in particular, where you don't care so much about having a low machine epsilon. And at the bottom is another example. This is from NVIDIA, the TensorFlow 32 format, which is not really a 32-bit, it's more like a 19-bit floating point number, somewhere between half precision and single precision. But my interest is in half precision because of what I'll talk about with Fugaku. Where could we use half precision in a weather forecasting model? Well, the IFS model is crucially dependent on a very expensive computational kernel, the spectral transform module. And this involves a few different operations, but basically half of this is the Legendre transform, which is used for the meridional direction of the spectral transform. For the Legendre transform, we still use a dense matrix-matrix multiply, a batch of gems, in other words. And this algorithm scales as n cubed as you increase in resolution. So it tends to become a bottleneck as we increase the resolution. Often the spectral transforms as a whole can be over half the cost of an IFS model integration above 2 or 3 kilometers resolution. It's a good target for half precision, not just because of its great computational expense, but also because the code underlying it is fairly compact. It's really just a few hundred lines of Fortran, incidentally, that we've just made open source. So a few years ago, at the end of my PhD, I demonstrated that it was possible to use half precision for the Legendre transforms. And I ran weather forecasts all the way up to 9 kilometers resolution. You can see an example on the left there. And I demonstrated that there's no impact on the weather forecast skill when we use half precision, although I did have to do some tricks in order to get around the problem of the very limited dynamical range of half precision numbers. Now, at that time, I didn't have any access to hardware that natively supports half-precision arithmetic, so I had to use software emulation. I therefore wasn't able to measure any kind of computational speed-up. But over the past couple of years, that has changed. We have now the first, as far as I'm aware, the first CPU that natively supports half-precision arithmetic, and that is the Fujitsu A64FX ARM CPU. Fugaku is a very large machine. It has 160,000 nodes, and each one of those nodes has a single socket with one Fujitsu A64FX CPU. This gives it about 540 petaflops of peak performance. Now this chip is shown in a diagram in the middle here, and it has an AH64 instruction set and 48 cores, which is quite a modest number, and these are split among 4 core memory groups, which are kind of like separate NUMA regions. It has no traditional DDR RAM at all, or even an L3 cache. Instead, we have 8 gigabytes per CMG of high bandwidth memory, HBM2, which is more or less exactly what you find on a GPU. And this is quite a low number. We only have 32 gigabytes of memory per node to play with. And this has implications, as I'll talk about later on. But as I mentioned, for my interests, it has native support for FP16 arithmetic. And Fujitsu claim that there's about a 4 times speed up from using FP16 compared with FP64, mainly because you're able to fit 4 times as many numbers in a vector unit. The A64FX has a very wide vector unit, about 512 bits. So I contacted Satoshi Matsuoka, who is the head of the Riken Center for Computational Science, where Fugaku is based, about a year and a half ago, and asked if we could get access to this machine to do some tests. This led to an official memorandum of understanding, a collaboration between RCCS and ECMWF, which started last January. So we're working with the Tomita Computational Climate Science Research Team. They're the ones who run those very high-resolution NICAM simulations a few years ago on the K computer. Now, I want to set your expectations low for this project. We have a very modest budget of only 20,000 node hours. Compare that with a typical Insight grant, which is about 500,000 on Summit. So we're not intending to run very long, high-resolution, high-complexity simulations. Really, we just want to run some initial tests on this novel CPU. So the key questions are, firstly, how easy is it to port an existing legacy weather and climate code to ARM, in other words, the IFS running on Fugaku? And then once we've got that working, how can we actually use FP16 in practice in a weather forecast model? How can we get around these low dynamic range problems that FP16 numbers have by algorithmic changes? And what actual speedups can we get from using FP16? So, this is the old slide. So let me just talk about the what's happened over the last year. The first 9 months basically involved porting of certain select components of the IFS model to Fugaku in order to gain expertise in the build system. And then starting about 6 months ago, I began to port the IFS model to Fugaku once the licensing was in place. And the porting process on the whole was actually pretty simple. The code was compiled within a matter of days. The difficulty came in optimizing it and making sure that it was making full use of the A64FX CPU. Unfortunately, we had a delay of about 3 or 4 months because we couldn't figure out how to correctly pin MPI ranks and OpenMP threads to the 48 cores of the A64FX. But we had a breakthrough about a month ago, and since then we've been able to run some scalability tests, and what you're seeing here is a summary of that. Now, weak scalability is used often without definition, so let me be very specific what I mean here. What we're looking at here is a series of runs of the IFS on Fugaku. Each one of those is 24 hours long, without any output at all, so it's just a pure benchmark. And as I increase the horizontal resolution from TCO79 up to TCO2559, which is 4 kilometers, I increase the allocation of computational nodes such that the work per MPI rank is approximately constant. And as a proxy for the work, I'm using the square of the spectral truncation. Now, all these runs have the same time step and the same vertical resolution, with the exception of the one on the far right, which has a slightly shorter time step. I'll talk about that more in a minute. Now, on the y-axis, we have the speed of the model, the simulated days per day, and you can see the orange line is a threshold, so we need to be above this in order to do operational numerical weather prediction. That's about 10 days in 1 hour. The first 5 points indicate, well, I don't look at these kinds of plots very often, but to my eyes, it looks like it's scaling quite well. We have a mostly flat line going from 126 kilometers on one node up to 8 kilometers on 240 nodes. 8 kilometers is the highest resolution that we run operationally at the moment. And so that's pretty good. But on the far right, we see an exception to that rule. The 4 kilometer very high resolution run, which was using 2,000 nodes, is performing slower than we expected. Now, this is not entirely a fair comparison because we used a shorter time step for this run, 4 minutes instead of 7.5 for numerical stability. And as a result, each MPI rank in that run is doing more work compared with the others. So we can compensate for this by inflating the number, and you can see that with the other cross above that. But it's still slower than we would expect from extrapolating from the other 5 runs. So what is going on here? Well, there's probably a few reasons why it's so slow, but I suspect this is the limited memory problem showing itself. We only have 32 gigabytes of memory per node on Fugaku, and in fact that's more like 29 because the operating system uses 3. And this means that, well, as we increase the resolution, the memory overhead per MPI rank increases. That means that we have to reduce the number of ranks per node as we go higher and higher. The first 5 runs are using 12 ranks and 4 threads per rank, so we're fully subscribing all 48 cores. But this run is using 6 ranks and 8 threads per rank. So we're still fully using all of the cores, but we've swapped some of the threads for ranks. And we know that the IFS prefers, on the whole, to have more ranks than threads. The sweet spot is around 3 or 4 threads per rank, and we are therefore running the IFS in a suboptimal configuration. But we have no choice because there simply isn't enough memory per node in order to run 12 ranks per node. And this is the kind of problem that we also encounter with, say, V100 GPUs. Those have either 16 or 32 gigabytes of memory. And it's the kind of thing that would be solved with the next generation of hardware. It's likely that the A64FX2, if there is such a machine in the future, will probably have 2 or 3 times more memory, and therefore this problem will be solved simply overnight by upgrading the hardware. So I'm not intending this to be a criticism of ARM-based CPUs in general. We're simply rather somewhat unlucky at the moment because this particular version does not quite have enough memory to be usable at high resolution. Now, what about FP16? Well, the use of FP16 on Fugaku is pretty straightforward, actually. And the Legendre transforms, which is the component I'm focusing on, at its core is a series of gem calls, gem taken from BLAS. So all that I had to do was replace the calls to SGEM, the single precision one, with this proprietary extension provided by the Fujitsu Scientific Software Library, FJ BLAS GEM R16. And the arguments to this subroutine have a kind of, are real kind equals 2. So this is a 2-byte floating point number, 16 bits in other words. So it was pretty straightforward to access the FP16 capability even within Fortran, which surprised me. On the right here, we have a benchmark of these gem calls, just the gems. So I've just wrapped the gems in with the profiling tools. And I've run it across a variety of resolutions, in this case up to 6 kilometers. The blue line is showing the performance for FP32, and the orange is for FP16. And I've split the results according to whether we are going in the inverse direction or the direct direction. For reasons I don't understand, there is a difference between these two. On the bottom, we have the ratio of wall clock time between single and half precision. And on the whole, we get about 2 times speed up from using half precision, which is quite nice. Though the speed up does depend on whether we're looking in the inverse direction or the direct direction. And it also depends on the resolution. So we do get the advertised speed up from using FP16 arithmetic. And this is probably because of the benefits for vectorization that I mentioned earlier. Unfortunately, we don't get such good results when we actually look at the model output. So in this case, I'm looking at a baroclinic wave test case. If you're not familiar with this, it's a standard way of testing dynamical core developments. So there's no physical parameterization schemes at all. We start with a zonally symmetric profile of winds with a jet in the northern and southern hemisphere and a temperature profile which is in balance with those. And then we apply small perturbation at initial time and observe how this baroclinic instability develops over a 10-day period. So here's an example from a 25-kilometer simulation run at single precision. We can see this nice packet of Rossby waves developing over 10 days. But when we use half precision in the Legendre transforms, we get some pretty odd results. You can make out a kind of baroclinic Rossby wave packet underlying that. But on top is superimposed some error patterns which are clearly projecting onto these spherical harmonics. On top of that, we also have a very spurious error pattern in the southern hemisphere, which is completely unphysical. And this is the kind of error that you see when you perturb the Legendre transform somehow, because it takes advantage of the north-south symmetry properties of the Legendre polynomials. So when you disturb that, often the errors project in unusual ways across the entire globe. So we're not there yet, unfortunately. Let me begin with some plans for the future. We intend to continue scaling the model up to, if possible, 1 kilometer resolution, TCO 7999. And this will allow a direct comparison with our summit simulations. So it'll be very interesting to see how these two different HPC systems compare with each other. They both take very different approaches to high-performance computation, Summit being predominantly a GPU machine. Also, if the budget permits, which I suspect it won't, I would also like to run some high-resolution coupled forecasts with NEMO. But this is conditional on successfully compiling NEMO with the Fujitsu compiler on A64FX, which is not something I've attempted yet. As for half precision, well, it just remains to carry on debugging. But as I said, I've demonstrated that it is possible with software emulation, so now it just remains to demonstrate that it's also the case for native hardware. Thanks for listening.
So there are some questions here. So first by Milan. How much of the memory is used by pre-computed Legendre polynomials? Could a recomputation of the Legendre polynomials free enough memory to circumvent the memory issues you face on A64FX? I assume that 12 cores with 32 gigabytes of shared memory share the same array of pre-computed polynomials.
That's a really great question. We have this unusually for very high resolution Earth system models, we rely on the spectral transform kernel. And in order to do this, this spectral transform, we have to store a very large array of the Legendre polynomials. And this is indeed often a problem when you go to very high resolutions. Potential solution, as Milan suggested, is to compute them on the fly on each time step, which sounds like a waste, but actually that can end up being faster than pre-computing them and storing them. And of course, well, not faster, but it reduces the memory overhead significantly. That is not something I've tried, but I do believe the IFS has the capability to do that, so that would be an excellent experiment to try.
Thank you. There are more questions, so then by Mario. Mario, you can also say the question aloud as you are there.
No. So for this baroclinic test that you also at the end, which is the approach that you are following to solve this kind of problems? Is maybe try to modify the algorithmical part, the code, or maybe use single precision for some variables?
Yeah. With the software emulation studies, I found it was very beneficial to keep some of the modes, the computations of certain modes, at a higher precision. And this is still good because you can perform the vast majority at half precision. You just keep the important ones at single precision. Unfortunately, that didn't work in this case, so it's a mystery to me at the moment. But one cannot rule out a simple bug at this stage. Yeah, but the way I would tackle it once I find time is to basically isolate both the direct and the inverse transforms to find out if only one of them is suffering from this problem. That's how I'll start. At the beginning, I was attempting a full complexity run of the IFS, and I realized that was just not appropriate for testing such a significant model change. So I found it much easier to turn off the physics completely, just to rule out that possibility. Yeah.
Thanks. And there is one more question. Maybe you can also, Nikolai, ask your question by yourself.
Yeah, it's more, just more philosophical, let's say, question. Since ECMWF have a lot of experience now with GPUs and ARMs, do you see, like, again, from your experience, that ARM can be a competitor or replacement for GPU, or is it easy actually to, because I mean for GPU is a lot of work, right?
Yeah.
For ARM we hope that it's not that much work to port the system. Do you see that ARMs are actually at this stage is a good alternative to GPUs, or GPUs are still on the top?
Yeah, I absolutely do, and I think it should be of interest to ECMWF. I've got direct experience with porting components of the IFS model to GPUs, and we have no choice but to do that in order to make the most of the EuroHPC systems, but it is very difficult. And I'm just one person, and I was able to get pretty good performance from Fugaku just through my own explorations. But of course, you know, Fugaku is a rather surprising machine in being number one on pure CPU technology, but it remains to be seen whether they can continue to get such a high spot without considering GPUs. It'll be very interesting to see what the post-Fugaku system looks like in 5 years' time.
So in principle, looks like the decision for EuroHPC go to GPU only, let's say, exascale machines is maybe not the optimal way for Earth system modeling.
Yeah, I mean, this is a somewhat political question, I suppose. We can do with GPUs. We can make use of GPUs, but it is hard. It's very hard for us, basically. Yeah, but we've had warnings for a decade now, so.
Yes, so thank you for the presentation. So I actually have two questions. The first one is about the numerical precision, because the community is split about the precision, and mainly for the climate research. Because what is your? I'd like to know your opinion about the lower the precision for long-term simulation of high resolution. Because and the second question is, how have you assessed the model accuracy? Have you performed an ensemble, and how have you assessed this? And is this applicable also for the climate studies? And sorry, the second question is quite different. You mentioned that your weak scalability is not good when you have a high number of cores, and you mentioned that probably the problem is about the memory. My question is, have you done the ISO efficiency analysis? From the theoretical point of view, we can analyze theoretically the behavior of our parallel algorithm, just making our ISO efficiency that tell us how the memory scale or grows when the number of cores increase. So have you made some theoretical analysis, the ISO efficiency analysis for the IFS?
I'll answer that first, just because I remember it. No, not really. And there's plenty to look into for those runs. They're very expensive, unfortunately, which deters rapid experimentation and repeated experimentation. And so you have to be extremely careful about where you place the profiling tools and such. But Fugaku does come with some very good Fujitsu profiling tools, which tell you, flop counts for different regions of the code. So that will be a very interesting thing to look at. In particular, with the IFS, the spectral transform does a global communication every time step. So it will be very interesting to look at the ratios of computation versus communication and seeing if we're getting any benefits from this supposedly very high, extremely fast tofu interconnect that Fugaku has. As for the first question, yeah, it's true. I've mostly swept that question under the rug by only looking at medium range prediction as my target, and that has been that's obviously an easier problem in a way than a climate simulation. So perhaps that explains why ECMWF is more keen on this than other centres, because the longest runs we do are maybe 3 to 4 months. That's the seasonal forecast. So yes, I do expect there will be issues when running multi-decadal simulations at such a low precision. I should also say that we do not use single precision for any data assimilation as well. That is pure double precision. So that is another community that is somewhat reluctant to use this low precision arithmetic, as well as the climate community. Yeah.
Okay, thank you. So let's thank Sam again.
Thanks.
It was, I think, very informative talk. As far as I understand, there's 20 minutes break now in the to set up for the online talks or something like this. So we reconvene in 18 minutes, right? 45.
And Sam, there are some questions also in the Google Doc, so you can, if you have time later, you can answer them. Thank you.
And only, sorry, as a practical detail, there is water there, and in the next break, there will be some fruit and cookies. But